Dr. Demoz on that as well. So with that, I'll pass it to Dr. Demoz. Thank you so much.
Thank you. Can you see my slide? Let me share that. Okay. Thank you for inviting me. I hope my slide is visible. Nikki, I'm good?
Yep. Oh. Okay. We can see your slide, and I have started recording.
Okay. Sorry, I'm not there. I am across the country from the West Coast today. Hopefully the connection goes smooth, but I'm delighted to be here and talk to you a little bit about both science and center history. I have been a postdoc at UMBC and then left and came back again. So I lead both GEST and GESTAR II. These are cooperative institutes at UMBC. And so I'm both a director and a professor. So I'm going to give you both sides of the talk today. So the first part is on the centers, how they started, where they are now, and where we might go. And the second part is a specific problem that I and my group work on that may be relevant to some of you, and I'm sure you have a solution for that. And so the first part on GEST and GESTAR II. Okay, why do I talk to you about that? I think maybe GEST and GESTAR combined probably are the biggest cooperative centers at UMBC. And with GEST, we have 25 years of history at UMBC doing a lot of the work we do in science, technology, education, and all that. And it's unique in the NASA world, in the contracting world, because that's the first center that tried to bring contractors into teaching into university life. And so it makes it very unique for NASA and very useful. On the other side, we take students into NASA. That's also good for the students and for NASA as well. So it is a unique center that has operated on its own space. So when did we start? I'm going to tell you a story. I know that's going to give my age. The first proposal was a single proposal to NASA by Harvey Melfi, who was retiring from NASA. There is a buyout call for retirement, 25,000. And we were in the field. I just got hired as a postdoc. And we were in the field, and he tells me he's leaving NASA, and he had talked to the UMBC leaders, department chair at the time, physics, and he said they're willing to bring me in. And he's going, I'm going to create this center. And the physics department, if some of you that know UMBC now, was a trailer at the time. And so that was his office. And he came in and he started negotiating, and he worked the proposal in a cooperative institute sense form, did an MOU. And that was the first startup. And then as he did it, there were 2 or 3 others that said, hey, I'm willing to come with you. Can we bundle this? So that's the seed for JCET. And the vision at the time was to create something that would be useful for NASA. NASA has so many scientists. And as you work as a contractor, you tell yourself, is this a career? Where do I get a stable position? And at the time, as some of you here maybe, I was an F1 visa holder. So I've always had that worry. So that worry into the scientist makes them less productive. All these excellent scientists, let's create something. That is how JCET started. And it got renewed and competed for something big that we used to call GEST. And so that transition occurred with Ray Hoff and Harvey Melfi and working hard. And we grew to 85 faculty. From 6 to 85, we had to adjust a lot of things, management-wise, and that set us into something large. If you trace, for example, UMBC's history in government contracting, you'll see the impact, you could see it there. And then around 2010, 10 years, we needed to recompete. The center, usually the centers are competed every 5 years, but if you get it the first 5, the second 5 was a given. And so we've got 10 years, but in 2011, we lost the GEST GESTAR Center. We lost the GEST GESTAR Center to the competition, mostly because of some employment satisfaction. Let me leave it. That was the main reason given, but there may be other reasons. And so at the time, Ray Hoff, the center director, wanted to retire. And that was the transition. I joined in 2014. We renewed JCET again for a larger cap. We're growing in faculty. And recently we competed back and brought back the old cooperative institute that was GEST that we lost in 2011. And right now we're about 165 research scientists. That's so the question is always you have to ask yourself what next. I'm sure iHARP is thinking 5 + 5, what next? And hopefully the history here may be useful in the planning. So right now we're 1 year into GESTAR and things are going. Hopefully we will keep it longer. And so who do we serve? All these centers, JCET, Joint Center for Earth Technology, GESTAR, Goddard Earth Science Research Center, they all serve the Earth Science Division in Goddard. And within that Earth Science Division, there are 3 groups. The first one, they call them offices. They deal with code 619, Terrestrial Information System. All of the data that's being measured is housed in there. And then the 610, or the Global Modeling and Assimilation Office, GMAO, is doing modeling. And then there's 2 other groups. The first one is the atmospheric group, that it deals with dynamics, climate observations, and chemistry. And the other one deals with cryosphere science, oceans, hydrology, biospheric science, geodesy, and what have you. So These three divisions each have a director, a lab of it, they call them labs, and then JCET, GESTAR, and a lot of other contractors deal with this. So iHARP, I take it, is working data on the cryospheric sciences part of it. So you can see there is a lot more that your tools can be applied to. So, okay. So a little bit of the highlights for JCET. I don't know if Chris is here. We have a group that deals with ice shelf. In fact, one of the branches of Project Science for Ice Bridge is a UMBC physics department graduate. Okay. We work with climate. An example from climate is the Discover satellite. It sits 1 million miles between Earth and the sun. So it can see the Earth as a whole, and you can even see the moon going around. If you've seen the video from that instrument, it's just amazing. Canley works on these topics. So the instrument scientists for the EPIC on Discover are both in JCET and are at UMBC. So there's huge data set in there. And there's a group, actually a large group, that looks at dust transport from the Sahara into the Amazon. And it's basically fertilizing the Amazon. Lorraine and several of our students that graduated out of UMBC are working on this topic. And recently, that's close to AI, Canley used a lot of cloud images from satellites and used machine learning to pinpoint where the ship tracks are. And he went back, retrieving that for many, many years back, as much as he can assemble the satellite pictures. And he came up with an estimate of what is the impact of ship tracks on climate. So these are just a flavor of some of the sciences that go in JCET. And a lot of them, I'm sure, could use some kind of machine learning training modules to make it better. Okay? So if you're interested in this, at the JCET website, jcet.umbc.edu, we have a running total of students working, models, and all sorts of snapshots of the science. And one thing that made me proud was we made it to the Time cover at one time. This is Chris's work and Nathan's when they did the ice bridge. And so that was big. So I show you to say a lot of the work that's going on in NASA is by colleagues from centers like this. Okay, so okay, what else did we do? One of the challenges, one of the goals we set at JCET early on was we need to have our own satellite mission to put UMBC on the map. As you know, satellite missions are expensive, but the payoff is great. So the first satellite mission that we submitted, did not get funded. We didn't give up. So Vanderlei here that you see in the middle started a CubeSat called HARP. And recently we've got an instrument that's going into another major mission, satellite mission called PACE. And HARP is hyperangular polarimeter. And it looks at the clouds and the atmosphere with so many polarization, with so much screen filters. And that means huge data set is coming through that. I cannot imagine doing this the way we have done everything, because it takes so much power to see even the data. So AI-based, machine learning-based analysis tool has to be created. Another interest for us was we knew always these cooperative centers are at the mercy of NASA. You can compete, you can lose, you can win. We're lucky, we've won several in a row, but we wanted to have something present always, something that is long-term where we can plan really good science. And that is why after 20 years of JCET, the Earth and Space Institute in the third floor of the physics department was established with NASA Goddard, director at the time here, and the president here. And the idea is to bring NASA into UMBC, into a center that UMBC fully controls. That is not cooperative institute. So the parallels, the lessons I see for iHARP in here is, iHARP is a National Science Foundation. Maybe you have 10 years. What then? Do you lose it? Do you keep something like that existing center going on? I think Oklahoma University has a center that they have established in that sense, looking at severe weather. And so for us, this would be a fertile ground for cryogenic, long-term pollution, and all of that could fit into a center that is wholly UMBC. So, okay, beyond the science, beyond the center, if it was not for JCET, the atmospheric physics program at UMBC would not have been established. Early on, all the courses were designed by JCET scientists. Most of the teaching was delivered. So the atmospheric physics program that has 6 faculty now and has 20 graduate students today present is almost equal to a number of departments at UMBC. So a lot of the courses, seminars, and the graduates also get hired at NASA. So that is a valuable input from that vision and that planning. We've got a group that works with GES and others also, but most interest to me is the graduate students every year that work they're funded through JCET to somehow make either a fellowship that we still provide that's competitive, but we've got like 13, 15 students coming in every year. And so that teaching side is important. So it's very good for the departments, it's good for the university, it's good for the students, it's good for NASA. So that's the way we plan. And we had quite an extensive bringing science to classroom, outreach activity, communicating science. We do workshops, visits. So there's several in here. The UMBC observatory still goes on. GEST is not funding it now. CSST, the astronomy under Don Engel, the director, is taking that lead. But we do quite extensive interaction with students. Okay. So a cooperative center, the way it was designed is to work on money that comes from NASA. It's usually, we don't, because it's not on campus, it's at 26% FNA, but the scientists are here and they do submit proposals through UMBC. That's at a full FNA. So as you can see, we have almost a 40-60 funding mechanism. The 60% NASA controls, the 40% is only owned on a grant and a competitive grant to NASA. And it's not only you're bringing the scientists from NASA and the money that comes with them, but you're also competing with them and bringing your own money. And I'll just give you a breakdown of the ranks. So at the center, you're doing both the human resources, the grant processing, and but it is good for UMBC. So a little bit about GESTAR. It has the same sort of model as JCET. UMBC leads the work. The UMBC, the lead. We've got Morgan State University as a partner, but we also have other partners: Arizona State, Colorado State, Penn State, SURA. SURA is the Southeast University Research Association. ERT is a small company contractor, and Northrop Grumman in there. All of those have a function. Sometimes you have to hire a person within a day or 2 days. And then the private companies help you manage. So you have to build your partnership. And I know iHARP has quite a large partnership, and I think that we're not dissimilar. We're pretty much doing. One highlight that makes me happy is out of 65 proposals submitted, this is months ago, 23 were funded. And that is close to a 50% success rate. By any measure that I have seen, that is a very good success rate in our field. And that tells me the scientists that are within GESTAR are quite excellent in the fields that they are working on. Okay, so the story for GESTAR continues. The take-home message I want you to get out of this is think institutionalizing the benefits of iHARP. 10 years comes so quick, 5 years comes so quick. Expand to other areas, the Sun, Helio, Astro, and the other centers beyond cryosphere. We've got a connection to all of them, and all this have data that just, I don't think we will analyze it in our lifetime if we don't use AI and machine learning. Okay, so that's generally about the centers I administer, and that's one part, and that's how my brain functions. Partly I am center administrator, partly I'm a scientist. So I'm going to take you to my science side of things. So I'm going to try to be brief, because, and I understand this is also a new area for a lot of you. So ask me a question at the end. The planetary boundary layer is the way I describe it. That's where weather happens. Now, climate is a slow changing mechanism. Weather is the rain that you have today. All of that is influenced by the lowest layer of the atmosphere that's close to the ground. That's what we call planetary boundary layer, okay? A lot of the pollution that you see is in there. The sun influences it. That means it has to respond to the sun's energy. Unfortunately, all of that data is very noisy. Very noisy, and I'll show you how good we do in measuring it. And so first, definitions. So the boundary layer that you see, the sun comes in and warms the ground, turbulence gets mixed, so heat goes up to some level, and you start clouds forming. And the sun sets, there is no driving mechanism of the air. So you would start to have sinking, stable layer. And then the sunrise, you go back again to the same. So when the sun is, we call it convective mixed layer. In general, planetary boundary layer is a general term for that layer. And this is probably the first 2 to 3 kilometers above the ground, okay? So that's critical, that needs to be measured, that's changing with time, and all of that. And that's where we live, that's important. So that is a conceptual model. I'll show you the LiDAR view. I'm a LiDAR scientist, so I shoot a laser up and I get scattered energy returned to me proportional to the number of junk there is, aerosol particle, dust there is. So this is an altitude to 5 kilometers, and this is time. So if I overlay a balloon based thermometer, this is a relative humidity. You see how the dotted curves correspond to the kinks in the return signal? And this is what we call potential temperature. And so you could see the kinks in these curves in humidity, in temperature, are responding to the activity into the dynamics of the boundary layer itself. So as you can see, the temperatures are every 3 hours, but the LiDAR is every minute. So the LiDAR gives you a complete picture of the evolution. The radio sound and the temperatures that you can fly give you snapshot at the time. Okay, so you have to assume what's going on. So what is happening in the nation is, like today, when you look at forecast, what we do is scale of forecast. Did the forecast turn out to be right? And in our language, meteorologists, they call it the threat score. If the threat score is high, you've done well. If your threat score is very low, you really are forecasting a 10%, 20% success rate. So if you can see at June, July, August, the threat score is very low. And that is because of the boundary layer knowledge. That's the weather, what the convection and all of that, the summer heat storms, thunderstorms, that's what they occur. And that's poorly understood. This is the colors here are several different models, and they are almost the same. No, not much of change. So the convection scale is very poor because we don't know the boundary layer well. And a recent study looked at the different things that we want to, sorry. In nature, there was, sorry. If you take the scale of the work that you do and model complexity on the y-axis, this is how many nodes you have and all of that. And right in here in the middle, convection and the storms like what you have today, you cannot get out, but you have to measure what's happening. Okay, so if you don't have data, you will not be able to do well in your forecast. That's the basic message of this slide is in the diurnal, in the storms where it matters to life and health and safety, you have to have observations and you have to assimilate them to improve your forecast. So how are we doing in the US with our observations? Satellites cannot see it because the temperature contrast that they look needs much bigger depths. So it's almost non-existent from the satellite. They can see the temperature of the sea surface or the ice, but they cannot vertically resolve it unless you have iCET 2 or a LiDAR. Radiosondes, the nation has been launching 2 radiosondes a day, maybe at 100 stations. And they launched them at 0, 0, and at 12, these red bars here. And that is the worst place you would launch for the boundary layer. It is at the start of the action and at the end of the action. So it doesn't tell you how high it is rising. In terms of the convection, the green bars, a lot of the convective activity, like today where you are, tends to be in the late afternoon, especially summer. And of course, the radiosonde are right after that activity. So that's poor planning, but they have to look at cost, they have to look at many things when they decided that. Every plane trip that you take, every plane is measuring temperature and doing sounding. And all of those planes send it to a database that's called iHARP, aircraft communication and stuff. But it has its own problem, but it's only good at airports. There are new things coming in, the GPS on your phone, and a lot of the GPSs you can do, but it does not resolve it. So where do we go from here? So the community has been asking for data for the agencies to get together and solve this. You don't need to read it, just put it here. Started in 1995. Some of you may not have been born. I said, this is critical. We need to measure it. In 1996, in 2009, the National Research Council convened, and they said, we need to do this absolutely. In 2011, NSF came in, said, we need to do this. And a lot of the NASA decadal survey asks for this. Bottom line is, we do not have a stable network or a measurement. And a lot of the data that the decadal survey, NASA decadal survey is forecasting, a lot of the money is in space missions in instruments, in techniques and algorithms to solve this problem. So if you see the decadal survey or any document, all of them talk, we need to do better. So I look at it from a different side of things. I know we have 1,000 LiDARs operating across the nation today. With a very little tweak, we could have a huge network. And I know we have a national network of radars. If we do the right algorithm, we can get this data. Okay, so imagine combining these two and having a very nice and neat AI machine learning code to come up with a national need. So I'll show you a big example. I show you this is called the ASOS, Automated Surface Observing Sites. It's operated by FAA, National Weather Service. Every dot that you see represents an airport of some kind. And what I show you, the picture of the instruments in that they've got rain, dew point, precip, wind, and then there's a cloud height, freezing rain, and visibility. This cloud height is a LiDAR that would give you the entire profile every 15 seconds. But because when they bought it, it was sold as ceilometer, cloud-based detector, not a profiler. The program written is to extract that cloud base and throw away all of the data. So this have been operating for a long time. So I'll give you an example. It shows, this example plot that I showed you is from a LiDAR. It shows altitude versus time. So the black dots that you see are edge detection algorithms that we, Milt Halem and our group has. So this is an edge detection thing. So you could see a lot of data in here, but it does capture this around 2 kilometers, how that thing is evolving, how that boundary layer height is evolving. This is one. So imagine doing 1,000 of this in an organized manner. It is a gold mine for model validation, air quality, fire, and smoke transmission, and all of that. Okay, so pretty soon, this data will become available. The only hang-up is whoever designed this decided it is safe and tamper-proof if they use a radio to transmit this into the Ethernet. So the radio has a very, very narrow bandwidth. So all that data is being thrown away. So we had a grant. I show you. I give you the references here that came from NOAA to study this and how we can do it. And there's a movement now. And just to give you an example, just look at the satellite image in the middle in Maryland. You could see the smoke transport, a very hazy picture. I don't know if it shows cleanly, but if you look at it from a LiDAR at the bottom, you can see the white line is the boundary layer, and the yellow hue that you see is all that smoke coming in. So beyond boundary layer evolution, you can also detect smoke. And when that smoke gets into the ground, you've got the black carbon count increasing, which means human health, air quality is affected. So if you have a smart detection mechanism to say, okay, this is the boundary layer height, and this is yellow stuff is something that's coming from somewhere, and you connect this to all the other LiDARs, you could improve the model. If you see the model in the green and yellow, it is missing the measure. The measurements say red, very high. Okay, the model says, maybe yellow. So that mismatch shows you. And data like this is a gold mine in forecasting. Okay, enough with the LiDARs. Now let me take you to the radars. I show you a map of radars across the nation. And this has been operating. If you look today, it will show you where the rain is. But there is what they call ZDR, differential reflectivity. And if you look at that, it will tell you at 15 at the sunrise, you can see this minimum in here. It can also give you the boundary layer height. A master student at Penn State have compared that with radiosonde, and it's a 0.9 comparison. So you have to squint. There's a lot of noise in the data, but it's not beyond doability now. So if you compare, if you add the radar and the LiDAR networks, I show you the radar from several cases on the side, on one side, the LiDAR, the one that says water vapor. It's not pretty, but you can combine this and you would have a very good base for satellites, for models, and what have you. This work has not been done yet. This is looking for a home, and there's pretty much both NOAA and NASA is focused on this. Even the Navy, pretty much every agency is looking at how do we do well in the boundary layer where it really matters. So more and more for the next 10 years, this is going to be a big issue. And so if somebody in iHARP has a solution, I would love to hear it. So take home message, part one is center organization, planning, where do you start, where do you go, what is your vision, and part two is give you a little bit of what keeps me sane with my students, and I think I would love to hear from you. I think I'm done. Hopefully we have time for questions. Thank you very much.
Thank you so much, Belay. Let's open it up for questions. If folks have, just unmute and ask the question or type in chat.
I can start. Hello, Belay. Thanks for the true overview on both the organization perspective and your research perspective. Since you are seeing AI ML can help you on boundary layer, can you tell some recent work has been done, because to us it's still a very new field. I mean, and can you give some examples how machine learning and AI is helping your research? Second question is that I think the noise, data noise is a common issue in many Earth data, including the one you're talking about, and including the iHARP data. And so what denoising approaches you have been using, and do you think the AI could play a role there? Thanks.
Yeah, I think, thanks, General. We have a grant from NASA, actually it ended, to look at how could you use AI machine learning with the LiDARs to have sort of a framework for a national network. We did one or two cases using, to me, I don't know not much AI machine learning. To me, it is edge detection, contrast, looking at that, and guided by the science. If you tell me the PBL height is at 6 kilometers, I say try again, because there is inherent physics that controls that. And so on my side, that's what I provide on the Jennifer Sleeman was the one that was running it. And she uses training models and try to see, okay, this is where all the edges are. Use the physics, where is it, you can flag them. So that's pretty much what we did. Denoising, most of what I did in denoising is using a wavelet analysis, trying to deconstruct, take the sun's noise out, very elementary, but it doesn't go to AI levels. A group at Goddard by Stephen Palm and his group, they have tried to use AI and use iSAT2 data to do global, because everything that I told you today is done from the ground. But 75% of the globe is water. You need something else. And the iSAT2 data is ripe for that. The Calypso data is ripe for that. We know what the physics is, but algorithm development has to come from somewhere else. That kind of overlap is what we use, and there's still room for doing that. Much more. It's just being started.
Thanks. I totally agree. I think that's also iHARP focus. One of the focus I have, we're trying to bring the domain knowledge to help the machine learning, because we think machine learning itself cannot solve all the problems. It has to be guided by the domain knowledge. Thank you. Yeah.
Yeah, thank you.
So I guess I can ask a question. The data that you talked about, the ASOS data and the LiDAR and radar data, is it mainly US data, or is it available for Arctic and Antarctic as well?
It is available, especially over Alaska. They're really, there's a dense network there because they have a lot of volcanoes and stuff that went on. The Europeans are doing much better than us. They're organized, they're saving it. And it's an interesting story. In 2008, I went to Germany with this proposal, and they made it happen within 3 years, and the whole Europe. In the US, it's still a struggle because the software is controlled by FAA, the instrument is controlled by National Weather Service. So they have to do a handshake for everything, and that delays things. But right now, I was told they have got all the approvals, and it's going to come.
Great. Thank you. I think there's a question, Shashi, from Shashi. What kind of AI neural network was tried by NASA scientists?
Yeah, way above my head.
You can talk more. I think there's more stuff.
Yeah, I am in physics, but if I remember correctly, Jennifer was using some database at Berkeley where she trains this, but all of the training data is also not a boundary layer data. It is something else. So I'm sure there is room for going there. So I hesitate to respond to that. The physics is a thing that interests me. And also to say, no, you didn't do it right. This is the physics. Try again.
So if I may add one comment, Dr. Demoz, first, thank you for a very interesting and informative talk. But the world of physics and the world of at least neural networks have come together in recent years in very beautiful ways. So you can actually put physics equations in the final layers to to reduce violations of laws of physics, so to say, like conservation of mass and stuff of that kind. So it will be interesting, if those problems, if the main concern was that the physics was not being obeyed by neural networks, there are new things that are happening and it may be worth revisiting.
And completely agree. I think it's something, all of this, even the NASA iSAT work is a simple edge detection thing that they did. So the edge detection doesn't see the physics at all.
Okay.
It just looks at contrast change. It's a former colleague of mine that did that. And for me, it required a lot of hands-on check. But if you can code the physics as you say and run both together, it would be nice to see it.
Okay.
And we have quite a lot of data to test that.
Okay, great. Now this will be a wonderful area to explore because this is a recent development, but it's growing fast.
Yep.
The intersection of physics and neural network.
Yeah, I would love to talk to you more.
That's great. I think one question that I'll try to explore a little bit more is many of these machine learning algorithms require labeled data, where you need annotations. For example, if it's a supervised learning algorithm where you're trying to find those boundary layers, you need to have some labeled data and annotated data to be able to produce the outcome. We are seeing something similar in the glacial layer annotation. It reminded me of your PBL, but the problem is that we don't have those annotations to begin with. But are there annotated images available for the PBL?
Annotation has to happen by somebody.
Yeah.
We do have quite a database to serve as training models, annotated models, and we have a small UCN network, unified kilometer network that we run, and we had several PhD topics on this. Yes, we can provide that. Thank
you. I think that's one of the things that we're experiencing too is, as Shashi was saying, and others have said before that Gian was saying we need to work with the domain experts to really co-create some things. And one of the big aspects is the labeling of the data before we put it into any model and correcting it, as you said. The physics tells you this is not correct. So those are really important. Yeah. This is going to be an iterative process until we reach somewhere. So when someone tells me, "Oh, I trained this with a set of pictures and cars and cats, and I'm going to use this," I cringe a little bit, but at least it performs to some extent. But I think Jennifer's did quite well, but you would have to look at an intervention and say, "Oh, this happens at this altitude, it cannot be PBL." It can easily be coded into the program itself too. But it is something that is new and can be expanded for sure. Any other questions? I think this has been really helpful, Dr. Demoz, and I've shared the information about all hands meeting with you and some other colleagues as well, and we would love to have folks from GESTAR, NASA, and others collaborate and visit us in the all hands. Yeah, I shared that, and there were folks from Colorado State University and others that were interested. So I told them it is open to everyone, so they may show up. Wonderful, that's great. And then we'll have follow-up discussions. I think a couple of threads emerged here, so we'll definitely have more follow-up. Thank you so much for visiting iHARP. Thank you. Thank you very much.
Thank you.
Thanks, everyone.
Bye, everyone.
Bye-bye.